I feel like we've been moving at a very nice pace. So the beginning of this year is hectic, like you already through it. All except for test one, kind of like bam, bam, bam. But now, you know, a little bit more of a breather. We got our feet hopefully underneath us as far as, you know, units, vectors, all that kind of stuff. That's what makes the beginning of the year so hard. I'm not only teaching, like there's so many skills that get packed in. And now, you know, you got the skills, hopefully, the problem-solving process, what is velocity, all that kind of stuff. We're going to keep using velocity, the entire, like velocity, acceleration, all that jazz. That's going to keep coming up. So I expect things to go smoothly. The pace to kind of, again, be like the pace that we've had for this week, which I think is at least not as fast as we started. And that's just how these things go. Okay, so last class, what did we learn? What do we do? Where are we at? So last class, we talked about work, you know, work, change, transfer of energy. We did this really great problem that had a bunch of steps, loved it. Thought it was like so many good concepts in this problem. Fantastic problem to make sure you understand. Because there's so many steps, which sounds like a bad thing. But because there's so many steps, we got to use free body diagrams. We did the force of that. We got to calculate work and connect, and then actually calculate that for kind of gravity. And we got to then take the derivative, kind of sort of this work to get the power. Like so many things in it. Just makes it a really good problem. To see if you have a holistic knowledge. So this is kind of like, if you can do this problem, that means you have a mastery over a bunch of different areas. Assuming, again, when I say you can do this problem without looking at the solutions while doing it, it does not count as being able to do a problem if you just look at how someone else did it and say, yeah, that makes sense. You're giving yourself a false sense of confidence. So I'll continue to remind you all of that. Anyway, all right, we talked about kinetic energy. Well, we talked about this. I told you all I am not going to ask you questions on the test about calculating your power bill. So we spent just a little bit of time on that. We did it, but not a huge deal. And then last class we ended with kinetic energy. Kinetic energy you gain from motion. We did a derivation, and we ended with the actual equation for kinetic energy, 1/2 mv squared. So today is all about kinetic energy and work. That'll take us some amount of time to get through. Whatever extra time we have, we'll roll into potential and conservation of energy. This week and next week are basically bundled together. This week and next week are kind of it's all energy. After that, we'll get to momentum. After that, we'll get to universal gravity and harmonic oscillators. But we're spending 2 weeks on energy. It's so important. Just like we kind of spent 2 weeks on kinematics, 2 weeks on forces, all that jazz. So, to start us off, so our equation for kinetic energy, I just gave you 1/2 mv squared. Let's go ahead and apply it. What has more kinetic energy? A 1,000 kilogram car going 30 meters per second, or a 2,000 kilogram truck going 15 meters per second? Reminder to you all, a good kind of conversion to have in your head, 23 meters per second is 60 miles per hour. It's just good kind of reminder. So is this realistic for a car to be going 30 meters per second? Yeah. That's like 75 miles per hour. Most of y'all do that, if not faster, on 417 or whatnot. So, again, it's good to kind of have an idea of how fast this is. This truck's going like 45 miles per hour. You don't need to know that, but it's just good to remember that these is real things. So is the answer, does the 1,000 kilogram car have the most kinetic energy? Does the 2,000 kilogram truck have the most kinetic energy? Or do they have the same kinetic energy? All right, and I'll give you all, I don't know how many people we have today. We'll check it out at 1:30, see how many people have responded. Reminder to you all, extra credit survey closes tomorrow at midnight. That is the only assignment in air quotes. You don't have to do that, but that is the only thing. The next quiz So the quiz for energy stuff, that's going to open today, and you have the next week. Remember, our quizzes always lag a week behind. I can't give you a quiz on something I haven't taught you yet, so that's why there's no quiz this week. I haven't taught you something in a couple weeks. Last week was test, so there's no quiz from that. All right, we'll go to 55. I think that'll be good. So 5, 4, 3, 2, 1. Now, there's a couple ways we can solve this. I'm going to do it the brute force way, which is literally calculate the kinetic energy of each one and see which number is bigger. Like that's, sure, why not? We got numbers, we can do that. So we'll do it that way. And the next problem, I'll talk about the other way after we do the next clicker question. So the kinetic energy of the car, fairly straightforward. So kinetic energy is 1/2 mv squared. You may every now and then see me put KE instead of K. They're interchangeable. Just when teaching high school, I always used KE, so sometimes you may see me accidentally slip into that. They're the same thing. Kinetic energy equals 1/2 mv squared. So if you plug in the numbers, that's 1/2 times 1,000 times 30 squared. If we do that for the second car, the truck, so that's 1, this is 2, 1/2 times 2,000 times 15 squared. And we plug both those numbers in. And we get 4. I'm going to use scientific notation because scientific notation is less writing for me. 4.5 times 10 to the 5 joules. If I replace the numbers, I get 2.25 times 10 to the 5 joules. All right, so clearly the car has a bigger number. Very straightforward as far as how to calculate this. The car, now the question is, probably the question may be why, because I did see some split answers. I see they're the same. So the next question is going to let us look at it from an equation standpoint. You could actually have figured this out without plugging it into your calculator if you understand the concept of the equation. So what happens to the kinetic energy if I have an object's velocity? Again, expect problems like these, y'all. If I change a certain variable, how does it affect another variable? Very, very, very useful and important questions because they test whether you understand the relationships between them. As this goes up, what happens to this? As this goes down, what happens to this? Very, very, very important things because when you're trying to come up with a design for something, you don't always have the time to do the math. Sometimes you need to be able to just kind of, okay, if I do this, what do I expect to happen? Will it get faster? Will it get slower? How much will it do that? All that kind of jazz. So, is the answer that the kinetic energy is twice the original? Is the answer that the new kinetic energy is 4 times the original? Is it half the original? Or is it 1/4 the original? We'll go to 120 on this. All right. In 5, 4, 3, 2, 1. And anytime I give you all a problem like this, if I change blank, how does it affect blank? The strategy is you write the equation and you rearrange the equation in terms of the thing that you want to see what. So, in this case, it's already set up for us. I want to see what happens to the kinetic energy if the velocity changes. Okay? So it's already set up in the way we want it. If instead I said what happens, my energy halved, what happens to my velocity, I will rearrange this equation for velocity. Sometimes you have to rearrange it in terms of the variable you want, just as if you were solving for that variable. But in this case, again, it's already set up for us in terms of the thing we want. So this is my original. It's already set up. Original mass, original velocity, fantastic. My new kinetic energy has the same mass, but my velocity is half. And this is where you have to be very, very careful. Whenever you're changing a variable, if that variable is being squared, then whatever is happening to it also needs to be squared. Really subtle, but you can just make up numbers to prove this to yourself. If my original velocity was 1 and my new velocity is half that, then it's half. If you plug in those numbers, 1 squared is 1. Half squared is 1/4. So what we do here, boom, we get this, we square that, and then the last step, you pull out the constants. You pull out the constants so that I have my original, there's my original, and then right in front of it, we have what happened to it. It's 1/4. This is how you solve these problems. Get it in terms of the variable you want, change whatever's changed, double whatever doubles, half whatever halves, plug that kind of in, pull out all the constants to the front, and yeah, we get it's 1/4. All right, so why, okay, last question I said you didn't need to do math. Let's actually revisit the last problem, but in terms of variables. So if we look at the last problem in terms of variables, we can also kind of think through this. I have my original problem, so the kinetic energy of the car, 1/2 mv squared. Some mass, some velocity. Then we have the truck. And what happened to the mass of the truck? The mass of the truck is 2 times, the mass is 2,000. That's 2 times 1,000. And the velocity is half the original velocity. So that's for the truck. And if we do this, what we end up seeing, we get our 1/2, we still have the 2m, and we have our 1/4 v. If we pull everything to the front, give myself a tiny bit more room. We pull everything to the front, we got a 2, we have a 1/4, and then we have our 1/2 mv squared. So I pulled that 1/4 to the front, I pulled the 2 to the front. Long story short, the kinetic energy of the truck is exactly half the kinetic energy of the car. All right, why is this meaningful? Why did I do these two problems? What I want to emphasize here is kinetic energy, velocity matters more than mass. It's squared. Once you kind of see that, it's like, oh, of course that meant, but this is really important. Something that is going faster will tend to have more energy than something that's going slower. You know, with caveats, if the mass is enough, then sure, like, you know, a bullet has way less kinetic energy than a truck, because the truck is massive. Well, actually, yeah, it should. We could do the math and prove that to yourself with the velocities, but I believe, I'm fairly confident in that statement. Even though a bullet goes really fast, a truck has such a big mass compared to it that it ends up winning. But this is a good point to prove with kinetic energy. Velocity matters more. That squared matters more. Subtle, small thing, but it's meaningful. It's really hard to get things going fast. That's kind of the punchline here. All right. Now, one thing we also mentioned, and this is kind of, so this is the last thing I kind of have to teach you all in this section. We started to solve for kinetic energy. We actually started with work. We said work equals blah, 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 a bunch of things. Work equals blah, 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 a bunch of things. Long story short, this is how we derived kinetic energy. W equals the change in equals the kinetic energy. This is how we derived kinetic energy. The last step here was that work equals 1/2 mvb squared minus 1/2 mva squared. This is called the work kinetic energy theorem. So our derivation for kinetic energy came from work. So kind of not fast forwarding, but going back to the next slide. Work is the change in kinetic energy. This is called the work energy theorem. Because there's work, and I guess energy because it's kinetic energy. I don't know. Well, maybe it'd be better if it was work kinetic energy theorem, but that's too wordy, I guess. Work energy theorem, work equals change in kinetic energy. Very, very useful for us. We'll do some problems with this. That's basically the rest of class is just me doing a couple, I say rest of class. That's what I'll be spending the next bit of time on, just applying this. All right, so what? What does this mean for us? What can we do with this? We'll find out. Work equals a change in kinetic energy. If my kinetic energy goes up by 5 joules, the work done was 5 joules. If the work goes down by 5 joules, my kinetic energy went down by 5 joules. Fairly straightforward. Whatever the work done, that's going to be my change in kinetic energy. Nice, simple relationship. Okay, so let's actually use it. Let's actually make it, so what? All right, so this problem, when released, a 100 gram, that's important, block slides down the path shown below, reaching the bottom with a speed of 4 meters per second. How much work does the force of friction do? Okay, so let's write down our givens. Our givens here is that we have the mass as 100 grams. Now remember, grams is one of those weird things where we wish that this was the base unit, but it's not. The base unit for mass is kilograms. So this ends up being 0.1 kilograms. Mass is weird that way, that kilogram is the base unit. There's 2 or 3 more givens depending on your perspective. See if y'all can figure out what the 2 givens are. Definitely 2 of them. Definitely 2 of them. Third one we'll kind of mention because we'll end up using it. But, oh, actually, okay, 3 givens. Definitely 3 givens. Definitely 3 givens. One of them's in the picture, not in the problem. What are they? All right, I'm going to point out the first obvious one. It's literally in the problem. We have a velocity of 4 meters per second. Now, you have to be very important here. Very, very final velocity is 4 meters per second, which kind of gives away what one of the other givens that we're going to have to look at. The final velocity at the end. If your problem has a beginning and an end, you need to be putting initials and finals. If my problem starts somewhere and ends somewhere else, there's an initial, there's a final. That's kind of just a good rule of thumb to have in your head. It started at the top, it ended at the bottom. Okay, so the one that was kind of hidden here, if there's an initial, or if there's a final, there's an initial, that's 0 meters per second. We assume the block started at rest. It didn't clarify that, but that's a pretty healthy assumption you can make. Again, in problems, there is certain assumptions you may have to make. It may not always be explicitly stated. For example, nowhere in this problem does it say anything about air resistance. We're going to ignore air resistance. Like, that's also a pretty common thing to do. Technically, we actually don't have to ignore air resistance in this one, but that's also one of those kind of things. All right. The other thing we know is we know where we know my y initial, which is 2 meters. And again, if there's an initial, there's a final. We know we end at the bottom. This one's a little, do I need to write this? But you can't get it. All right. Lots of givens. What are we solving for? The work, but not just the work, not just W done. The work due to friction. You could put WF. I wrote the word friction just to make it clear. Okay. Whenever we're talking about work, expect to draw a free body diagram. Whenever we're talking about work, expect to draw a free body diagram. Because work equals force times distance times cosine theta. Like, we need that force. Technically, it's an integral, but I've kind of told you all this already. If I don't give you a function for work, you're not going to have to integrate it. Okay? If I do not give you a function for work, you're not going to have to do an integral. Okay? All right, so let's draw a free body diagram. Here's my block. You all think about what forces are acting on this. Hint to you all. kind of complex. There's technically like 3. We're going to collapse 2 of them to get like, technically there's 3. Which is kind of funky, but it'll simplify to just 2 of them. And this problem is going to be kind of an exercise in remembering conservative and non-conservative forces as well. Anyway, it's going to look worse than it actually is. As you do these problems, you start to realize we can take some shortcuts conceptually. So if we draw a free body diagram, you should have gravity going down, you should have friction going this way, and you should have the normal force going this way. Those are the 3 forces. Now, I will straight up tell you we're not going to worry about normal force. Why? Normal force is perpendicular to the direction I'm moving. The normal force is not doing any work. The direction that this thing is moving is this way. Okay? So I'm drawing this free body diagram, but I'm going to straight up tell you all, like I only drew this to show that gravity and friction are the things that matter. I'm straight up drawing this to show you all that gravity and friction are the things that matter. Why am I saying all that? Because we have to account for both of them. And again, right now, everything I'm saying, I'm kind of giving you all the concepts. As you do this more and more, you're going to realize this simplifies way simpler. You're like, oh my gosh, does this mean I have to find angles? Does this mean I have to like integrate over the is this one of those inclined plane problems and I have to do all that nonsense? No. No, you don't. It's a wonderful thing. Why? Let's go back to our slide where we talked about conservative forces. You all remember when we did these clicker questions and I said, hey, I push a box across the floor. Does it matter which path I took for friction? The answer was yes. The path you take for friction matters. And then the next problem was, does the path matter for gravity? And the answer was no. The path for gravity doesn't matter. It doesn't matter how bumpy that road is. It doesn't matter how weedy that road is. The path for gravity matters. Let's take those 2. So we have conservative forces. Path doesn't matter. Non-conservative forces, path does matter. How does this matter to you all? Friction, path matters. Gravity, path doesn't matter. That's kind of the most important thing you need to have in your head. Why does that matter? Why is all that useful? Going back to this whole problem we're solving, here's a shortcut we end up getting. What is my work done? Let's just put this a little simpler. We have the work due to gravity. And this is going to throw you all for a loop. The work due to gravity is going to be a positive number. And you may be like, but the force is downwards. Correct. But which way is my box moving? Downwards. The force of gravity and the direction it's going line up. So the work due to gravity is positive because they line up. When it comes to work, you care about the direction of the force and the direction it's going, and that determines positives and negatives. Are they lined up? Positive. Are they opposite directions? Negative. So gravity is pulling this thing down the hill, which is the direction it's going. So great. Work due to gravity is positive. Work due to friction is negative. Why? The force due to friction is up the hill. The direction it's going is down the hill. Pro tip, y'all, the work due to friction is always negative. It is doing because the force and the direction of motion are opposite to each other. Always, always. Every problem, for the directions of things moving and the friction are always opposite to each other. Okay, so I set this up. WG minus WF. Here's the cool thing. I didn't ask for you all to find the force due to friction. This problem doesn't say what's the force due to friction. So yeah, friction, the path matters, which means calculating it would be an absolute nightmare. Because look how bumpy that is. That's awful. So also, I'm probably not going to have you calculate the force due to friction in these problems, because to do that, you would have to know the exact path it takes. And look at this picture, y'all. All these little bumps, Awful. Nightmare. To solve that, you'd have to integrate it, and I'd have to literally give you the function for that path. I'm not going to give you the function for that path. That's just a mess. So great news. We don't need to solve for WF. Like, we don't need to find the force due to friction. This is good. We're happy with this. We don't need to do any extra. What about gravity? The path doesn't matter. All that matters is where I start and where I end. Where do I start? At 2 meters. Where do I end? At the bottom. So what gets funky here is when we take this for gravity. So let's just go ahead and do the work due to gravity. Work due to gravity is going to equal mg, that's the force due to gravity, that's F, times the distance I went. And this is a really subtle thing. So displacement, technically displacement, final minus initial. Why does that matter? I end at the bottom, not the top. So it's 0 minus 2, not 2 minus 0. Again, that negative sign's gonna matter. I told you all it's positive to begin with, and that is true. The force and those are the same way, but then when you do them, what happened, work due to gravity, ends up being a negative here. Okay. So anywho, negative 2 times 0.1 times 9.8 gets me a number. So negative 2 times 0.1 times 9.8. Fantastic. Negative 1. All right, let's put all this together to see what the heck am I building? Because at this point, you're probably like, oh my gosh, so much is going on. And at the end of this, I'll summarize to you all the important things and how you're going to actually engage with these problems. I've kind of been touching on all the concepts because I don't want us to forget them. But I will also tell you all this problem simplifies very nicely. So let's put all the pieces together. One more equation that we need. Work equals the change in kinetic energy. Again, we're going to end up needing that as well. Yeah.
So you said for gravity is going to be a positive number. So how come we wouldn't do negative 9.8 so that way your negatives cancel and then it is positive?
So I said it was positive. So here when we set it up, we had to put it as positive. But if I was lifting my object, then I would get a positive at the end. So we had to define it. So this work was defined as force times distance.
Okay.
And so we had to recognize force and distance are the same direction.
Oh, okay.
So regardless of whether the thing's going down or up, we start with a positive, and then we have to actually plug in the things.
Okay.
And then it ends up spitting out a negative. Yeah. So there's kind of 2 levels here. Conceptually, we had to think about whether it's positive or negative, and then we had to plug in numbers, and it ends up also doing stuff to it.
Okay.
Yeah, and we'll actually see, we're seeing a little foreshadowing today. That work is the negative change in potential energy, but we'll get to that when we get to that. All right, great. What are we going to do? We're going to take this guy and put them together. The work of gravity minus the work of friction, and we're going to see if I made a mistake at any point, equals a change in kinetic energy, 1/2 mv final squared minus 1/2 mv initial squared. And at this point, we can just put in things. This is ultimately what we're doing. And you know what? Again, one more step. Let me think through that this is going to work the way I want it to. We'll just see. Make certain I did do a good job with my positives and negatives. We're going to find out at the end. So far, I'm feeling good because I'm following all the rules, but all right. So work of gravity was a number, negative 1.96. Ready? Calculate that. Minus the work of friction equals 1/2 m. We know the final velocity. And this one we know as well. Now let's put the actual mass there. Put the actual mass there. This term doesn't matter because it's 0. Boom, that's gone. And it's just math. We finally reached the final step. So this is really the magic sauce here, y'all. This is really what it comes down to. And again, we had to be careful. We really had to be careful with this whole thing here. Yeah.
Why are we not finding FGX?
It's a good question. So, because path doesn't matter, when it comes to gravity, when it comes to the work due to gravity. We just need to figure out how much up and down it went. We didn't care what path it took down there because it's not a vector. Work is a scalar, which means we don't have to worry about x and y, which is awesome. We only care about, when it comes to gravity, where I start and where I end for work. For work, we only care about where we start and end. Yeah.
Is that the reason we don't need cosine for the angle?
Yep. That's also why we don't need the cosine of the angle. It turns out when it comes to gravity, all that matters is height. All that matters is height, because it's a conservative force. The amount of work required to make my calculator do this whole windy path down due to gravity is the exact same if I just dropped it straight down. We don't worry about, and it's just one of those little tricks that comes out,
I thought the work due to gravity was positive.
It was, but because the distance, so distance is final minus initial, our final was lower than we started. So when it started positive, and then we actually had to do the subtraction here. Yeah, it's a good question. All right, so let's see if this all works out and see if I did a good job with my positives and negatives. So if we rearrange this, the work due to friction equals 1/2 times 0.1 times 4 squared plus 1.96.
Would it be negative at the beginning?
Yeah, let's see. Did I? Boop. Bump that over. Bump that over. No, let me see. I need to add that over. It makes everything negative. That's fine. There's like a negative in front of all of this stuff. Is what it ends up being. If I add that over, yeah. Anyway, let's do the math. All right, and I'm going to check my solutions because, again, I want to make certain I'm not lying to you all about this whole positive, negative nonsense. Make certain you plug in the right numbers. I actually put times 0.14 squared. All right. 2.76 joules. Okay. And I'll straight up tell you all, this problem that I just did is going to be way easier. Is something off with the answer?
I'm just confused on why the whole thing's negative, because I just added the W sub F and then minus the 1/2.14 squared.
So if I added the 1.96 over, this whole side's positive, but I still have negative WF. So the negative still is there. So I added 1.96 over, and then I'm still left with this negative sign. That still exists.
Okay.
Yeah, I could spend more time on that, but that'll be one of those. All right, so let me think through if this is everything I wanted it to be. There's a quick calculation. I'm going to show you all when we get to conservation of energy. This is much easier. Is something off?
No.
Okay, because I'm not paranoid about this, but yeah, what's up?
I'm just really bad at the positive, negative stuff in general.
Yeah.
Run through one more time,
Sure. So let me do a quick calculation because I'm going to show you all. There's a shortcut to doing this that we're going to learn kind of this next week. That's going to kind of make this easier to understand. Okay, and yeah, I flubbed up something somewhere with the negatives. Sad job, me. All right. So, yeah, I definitely flubbed the negatives here somewhere, so my apologies, y'all. Let me go ahead and show you what it's going to end up being, because the reality is we're not going to do all this mess, okay? This is kind of a good foreshadowing of the future. So what we're going to learn eventually,
Is negative work ever possible or no?
is negative work ever possible? Yes. Negative work means I've decreased the energy of the system. I've taken away the energy in some form. So positive work means you've added energy. Negative work means you've taken away energy. That's why friction is always a negative work, because it's always taking away energy. Because if you push a box, it should keep going. So, let me give you all the foreshadowing. This problem, honestly, is better to do when we cover conservation of energy. Otherwise, we end up in this whole weird positive negative land. And I'll tell you all, I made a mistake in terms of this positive negative land that we're in. Silly job, me. This one should have been a positive. Let me show you all what's going to happen. Let me show you all how you will actually end up solving this problem. The reality when it comes to the test. We are going to learn, so this is a nice foreshadowing of next week. We're going to learn that there's something called potential energy. We're going to learn that there's something called potential energy due to gravity, and it's going to look really familiar. It's MGH. You all have probably seen this in middle school, high school. At some point, you've probably seen MGH. In fact, you've probably seen everything I'm about to just show you. The energy I start with equals the energy I end with. Assuming energy is conserved, which is always true. So what we're going to learn is that the potential energy I start with plus the kinetic energy I start with equals the energy I end with plus the kinetic energy I end with. Okay? So this is good. This is good time. This is going to help us solve them. This is ultimately how we're going to approach these. The way I did it, the positive negatives ended up even getting out of my hands. Why does this matter? MGH initial plus 1/2 MV initial squared equals MGH final plus 1/2 MV final squared. Okay? Ideally, this is the case. This is assuming no friction. This is assuming there is no friction. The potential energy and the kinetic energy I start with is going to equal the potential energy and the kinetic energy I end with. Okay? Assuming those are the only types of energy present. Why does that matter? How does this play into this problem? Why do we care? If we look at this problem, I have no kinetic energy to begin with. I have no kinetic energy to begin with. I have no potential energy to end with. I end on the ground. Literally the height on the ground is 0. My velocity initial is 0. Okay? This term is 0. This term is 0. They multiply and equal 0. So let's kind of then take the next step. Let's put in the numbers, and we're going to see that the equation I just wrote has a discrepancy. And that's going to help us reveal how we should solve this problem that we just did. How we avoid this whole positive, negative, what's going on. Again, honestly, this whole work thing with it, that's a harder way of doing it. So I'm going to show you all the reality of the way we're going to do this, which means I should have done this problem after we did conservation of energy, but you live and you learn. All right, so point one, and you know what? Fun fact, y'all. Both sides have mass. So guess what happens to the mass? It's gone. We don't actually need to plug it in. It's on both sides. It cancels out. So that's nice. All right, so why do we care? I want you all to see the problem that's going to arise in this. What I am writing here is false. This statement is false. So this is us discovering kind of what's going on in this problem. How I kind of work through it to kind of check my answer. Because this is the way you're actually going to solve these. All right, hopefully you realize that this is not a correct answer. False. That is not true. Okay? And I took away the mass. I apologize. We did need the mass here. My apologies. My apologies. We do need the mass. It looks like it cancels. It does cancel if friction's not present, but we need to put the mass in. That's important, so my apologies. You may see it on both sides and say we can cancel it, but again, we're going to see why. All right, so same thing, just everything shifts. Oh, my calculator. All right, whatever. 1.96 equals 0.8. Okay, so we look at this. Obviously, that's not true. Hopefully everyone in this room looks at that and says, yes, 0.8 doesn't equal 1.96. So what's the next question? Where did the energy go? Friction. That's how to actually solve a problem like this. This is kind of the easier way. You don't need to bother with positives, like having to worry about positives and negatives and making the mistake that I did. In this problem, we see, where did my energy go? Went to friction. This is why the M didn't cancel. Work due to friction is energy. Work is the transfer of energy, how much my energy changes. So this is, again, ideally I would have done this by actually conservation of energy, but straight up, this is how you are going to solve these problems. So it's going to kind of show you this. We're going to do a lot of stuff. It's not, the more we do this, the easier it gets. But literally, this accounts for why I should be going faster. I should be going faster. Why am I not going faster? Because of work. And then if you just do this quick subtraction, you get the work of friction is 1.16 joules. I lost energy. I didn't actually lose it. It went to friction. It went to friction. Okay? So anyway, we're going to see more of this. This is really a lot of what we're going to be practicing next week. But it's kind of good. The key punchline here is if your potential energy and your kinetic energy in the beginning don't add up to equal your potential energy and kinetic energy at the end, something else had that energy. In this case, it's friction. Yeah.
Okay, I'm hesitant to ask this, but wouldn't it be negative?
Yeah, so it's a good question. Is the work positive? Is the work negative? I mean, really the question is, where do you put work? Do you put it at the beginning or do you put it at the end?
Yeah.
Probably we should have put it on the other end. Is my thing broken? Yeah, it's, oh. All right, do I have a ghost? No, no ghost. Yeah, I probably honestly should have put the work on this side instead, which at the end of the day makes it, but I can't erase things, so that's fun. Anyway. All right, so I'm going to save this real quick, and I'm going to kind of put the big punchline up here, and we'll do one more problem with this conservation of energy thing, because the reality is conservation of energy is the bee's knees. We're going to spend a whole week talking about it, because it's so good. But yeah, work, all that jazz. It really just boils down to, if I don't give you a function for work, you end up often doing conservation of energy. So that's good to know. All right. Let's see. So let's look at this last problem. But yeah, would have probably been negative. Put it on the left side, all that kind of jazz. Apologies, y'all. A little bit messier than my usual classes, so I apologize for that. But I will make clear what's clear. Okay. So, forces that you all want to remember, you got mg. We're going to look at this kx1 in just a second, and we got friction. But the reality is I'm not going to have you all find. There is one problem set problem where I have you find force due to friction. It's good to try it out, but I'll be straight up honest with you all. If I give you a problem involving work, and I ask about friction, I can almost guarantee I'm going to say, what's the work? I say almost guarantee. I will ask you for the work due to friction, not the force due to friction. Because the path thing is messy. The path thing is messy. Okay. So, let's look at this next one. This is the one I probably should have done. It's a bit more clear cut. When a 3.0 kilogram block is pushed against a massive spring of force constant 4.5 times 10 to the 3, the spring is compressed, it's released, it slides 2 meters. I'm trying to decide if I even want to do, again, if I want to go through all the messiness or if I want to just jump into conservation of energy. This is going to be shocking, y'all. We're going to skip the conservation of energy. Sounds stupid. The reality is we could do this problem again and we could deal with the positives and negatives and we could do an integral and that we could have so much fun. Or I could jump to conservation of energy and show you didn't have to do the integral. We don't have to deal with the positives and negatives, and life goes on. So I'm going to choose the latter. And I'm going to straight up tell you all. And you know what? Maybe I'll probably even give you all an extension on this quiz that's coming up. Because the reality is conservation of energy is such a powerful tool that all this force and distance stuff really is just preparing us for conservation of energy. And you'll end up predominantly using conservation of energy. Okay? So let's kind of jump into that. Again, apologies for the messiness. This is one of those things where sometimes you don't realize the best way to teach it until you've done it once. So future generations won't suffer as much as you. I apologize. But that's how it sometimes goes. All right. So we're going to talk about potential energy, relationship between potential energy and work. Starting energy must equal final energy. Energy transforms. Yeah. All right. We got 4 minutes, so I got to be quick. There's some things. System. Great. Let's just get to potential energy. I've been using it this whole time. I want to at least end class telling you what the heck potential energy is. We'll see what I can do. How do you make an object gain potential energy? Make it faster, lift it higher, slide it on the ground, warm it up. Look, I've already told you all the equation for this. So I'm just going to put it here. We're kind of working backwards. You all have hopefully seen this equation at some point in your life. If not, there it is. We're going to see it again in a bit. But because I've kind of flubbed things, I'm going to guarantee that you all get these clicker questions right. How do you make it gain gravitational potential energy? There is 3 variables that affect it. Mass, gravity, and height. If you are not changing one of those 3 things, you are not changing its gravitational potential energy. Do any of these have to do with mass? No. Do any of these have to do with the strength of gravity? No. So the answer, again, lift it higher. I'll give 5 seconds for everyone online. 5, 4, 3, 2, 1. Oh, yay! We did it. Oh my gosh. I don't care. They got it wrong. Sucks to suck. All right. Not even mad. All right. So great. We've done this integral a bunch of times. This is the one we've done for the problems with the work, and is it positive, negative, and yeah, it's so good. What's the integral of mg dy? Question to y'all, does mass depend upon height? No. Does gravity depend upon height? No. So if we integrate this, what a challenging integral. And again, just to keep things moving, what is the integral of dy? Why? Wild. Absolutely wild. So lo and behold, it's this answer. Again, we're just kind of chucking through this because I really want to get us to conservation of energy so we can actually do the problems that I originally proposed to you all. mgy final minus mgy initial. Let's see how we're doing. Oh, they got 5 seconds. This would be kinetic energy, but not really. We're going to 15. 4. Again, you can see the effect of the delay. Thank goodness you all are in person. All right. Good job, people that were here. You did it. You got the right answer. I'm proud of y'all. All right. Okay. This is a really philosophically interesting say philosophically. This is not philosophical. This is a very interesting question that we'll answer next time. Bam, here's the equation for potential energy. We did it. We got to potential energy. It's mgh. But like I've already said it a bunch of times. You've already seen this a bunch of times. But this emerged from that. And again, I'll be honest with you all. The quiz, I will give you all a slight extension on this upcoming quiz. Because the reality is, so like to Tuesday, that's probably what I'll do. I'll bump in an extra so the quiz, say extension the quiz. The quiz is already not due until Saturday. So this whole work stuff, the quiz already isn't due to this Saturday. I'm going to bump it to this Tuesday just due to the reality of a lot of these problems benefit from conservation of energy. So this way we get through conservation of energy as well. All right. Apologies for the messiness, y'all, but just goes to show sometimes there's an easier way to solve problems. And if you don't know that easy way, it's just bleh. Thanks for dealing with my fumbling, y'all. I'll see you on Monday. Conservation of Energy is going to be great. You're going to love it. It's one of the coolest things ever. It's so convenient. Yeah.